Now the experiment which I am going to perform is to determine the specific rotation of cane sugar in water using a biquartz polarimeter. Okay, so what we have to do is we have to find the specific rotation of cane sugar which is dissolved in water, and with the help of a biquartz polarimeter. So apparatus which I am going to use is a biquartz polarimeter and ordinary source, light source, and we need to some physical balance. I don't need physical balance. Source of light, measuring cylinder, a beaker, a glass rod in which we are going to fill my cane sugar or water, and the main apparatus is the biquartz polarimeter. Okay, so what I can see is that this is my you can see this is my source, light source, which we are going to use is a sodium lamp, and then what I have is my biquartz polarimeter. You can see that this will be towards the source, and this is our eyepiece, and this is the slot in which we are going to place our tube. And you can see the two tubes are like this. One will be filled with the water, and the second will be filled with the sugar solution. So these tubes are going to be inside this slot. Okay, let me open it. These are going to be inside the slot like this, and then we will shut it down. Okay, so this is the whole biquartz polarimeter which we are going to use. The scale, you can see here, the scale of the biquartz polarimeter is, there are two scale. One is this scale, this circular scale, and one is this vernier scale. Okay, so this circular scale starts from 0 and then it goes up to 360, 20, 10, 20, okay, 40, 50, 60, and so on. It goes up to 330, 340, and 360. So now you can see that there are two scale. One is this circular one, this and this, the circular one, and the one is this vernier scale which has 0 to 20 division. So since this is a circular scale, so the least count of this circular scale will be, because it will go from you can see 0 to, what is this, like this is 40, 50, and 360. So there is a 10 division between, so one degree is equal to 1 degree, and then I can see there is 10 division on the vernier scale. So if I compare it with the, so if I put it to 0, so you can see, let me make it clear that the 10 division on the vernier scale is equivalent to the 9 division on the main scale division. Okay, so this is circle. So you can see the scale, this scale is like 0, 10, 20, 30, 40, and so on, 350 and 0, and this will be 360. So, and you can see I can move this. So if I fix it to 0, a 0 scale to 0, then you can see that the 10 scale on the vernier is equal to the 9 division of the main scale. So main scale is because circular, so the least count on main scale, you can say there is 10 division is there. So 1 division is equal to 1 degree. Okay, and it is divided into 10 smaller parts. So the least count will be 1 by 10. So this will be 0.1 degree. Okay. The formula which we are going to use to find the specific rotation is, you can see, is alpha, and this is T at temperature. So then the specific rotation alpha T of the solution at some temperature T. Naturally, we are doing this experiment at room temperature, the T will be at room temperature. This is theta V by ml. So theta is in degree and L is in decimeter, V is in cc, and m in the gram. So basically M is basically the mass of the cane sugar which we are going to dissolve in the water of certain volume, okay, and L will be the length of the tube which I have shown you, in which we will fill the water or the cane sugar solution. So this using this this M will be fixed. So what we are going to use, M value of M, the mass of the cane sugar which we are going to dissolve in this much of volume, and this will be the length of the liquid which will be filled in the tube, and the theta we will find out during the observation. That will give us the rotation of the plane polarized light while it passing through the solution of the sugar. Okay, the schematic of this you can see here is in the Biquartz Polarimeter is that this is my source, as I have told you, that is the sodium light, and then we have a lens, and then we have a polarizer inside it, and then biquartz plate, and this tube which we will put inside this gap which I have shown you. Then after then we have an analyzer, and then we have the eyepiece. So we have source, lens, polarizer, biquartz, then we will put the tube, analyzer, and all these analyzer, biquartz, and this analyzer and polarizer are there inside. Just we have to put this tube in the Biquartz Polarimeter. So let's try to find the observation table. So observation table is like you can see is, first as an observation we have to know the mass of the beaker. Beaker means like in which we are getting our water, mass of the beaker per the sugar cube, okay, and the volume of the solution, what we are going to take the volume of the solution, length of the tube which I have shown you. This is my tube, you can see the length of the tube we have to measure from this place to this place, because this will be the length of the water volume which we are going to fill in this, using this volume of the water and the sugar cube. And the temperature, we are working at the room temperature, okay. So the value of the main scale division on the circular scale I have shown you, this is 1 degree, and the vernier coincide with is like the vernier is 10 division is coinciding with the 9 division, as I have shown you that the 10 division of this vernier is coinciding with the 9 division of this. So the least count will be 1 by 10, this will be 0.1 degree. Okay, so table of observation is like this. We have the first position of the analyzer and the position of the analyzer 180 apart from the first setting. So and then this is the tint of passage obtained in the two halves of the field of view. One is clockwise and anti-clockwise. This is main scale division, then the vernier scale total, and similarly for the anti-clockwise. And then the tint of passage obtained in the two halves of the field of the view, similarly clockwise and anti-clockwise. So we have to find out the tint of passage. So what is tint of passage? I will tell you. Obtained in the two halves of the field of the view. So what happens during the observation? What happens? Let me tell you. I'll start with. Now you can see I have put this biquartz spectrometer and in front of this source. So you can see that this is my source, and then we have a lens and polarizer. So this side I have my source, and then I have a lens, and this we have a inside we have a polarizer and biquartz plates is there. Then on this slot, in this slot I will put the tube, and I will cover it up, and then this other side we have analyzer and the eyepiece. So this side I have an analyzer, and then I have eyepiece through which I have to see. So the first procedure is that I'll cover it. There is no tube inside it. I'll cover it and try to see through the eyepiece, and using this rotation of the analyzer, what I will see that I will see a bright spot that will be half will be lesser bright and the other part will be more brighter. So by rotating this, I have to find the position of the equal brightness. So what I have to find it, that when I will see it, I will see that there is a spot. You can see that in half, that this could be less brighter than this. So what I have to do by rotating it, I have to find that this to be of same brightness. Okay, the two halves has to be of same brightness. Okay, so then by rotating this, I have to find the position of the same brightness. Okay, and then I have to note this, fix this position. Then what I have to do is I have to take the one with the water, filled with the water, simple water, and then I will put this tube inside this here, make sure that it fits properly, and then I'll cover it. Then what I have to do is, then I have to look for the passage of tint, because as I have told you that in the observation table, I have to, for the first position of the analyzer, tint of passage obtained then at two halves of the field of view. So then I have to look for the tint of passage. So when I fill this with the water solution, then what I am going to look is, I am just going to look from the eyepiece here. Then what I will see, that there is a spot which is, one is black and one part is white. Okay, so then what I have to look it for, when I will rotate it. So I will very slightly move it down. Okay, clockwise, because what I am doing is clockwise rotation. Okay, so I'll move it the clockwise, and seeing into the eyepiece, what I am going to look it for, that after certain rotation you will see that this position changes. The other side becomes black and then it becomes white. So while going from this position to this position, so there in between this there will be a tint of passage. There will be a tint of passage. Okay, in which I am going to have a position which will be of equal brightness. Equal brightness. So this will be somehow when this black is on white is being exchanged. So in between there is a position which is called a passage of tint, where you can see a equal brightness. So I am going to look for this position. So while I am moving this and looking into this eyepiece, I have to find this position where there is a change of position and of the equal brightness is there. So I'll stop at this position, and then I'll look for the main scale division. So like if I say this is my 40, 41, 42, like main scale is 42, and then I'll look for which main scale division, which one nearest scale division is coinciding with the main scale division. So let's say some like 6 or 7 is coinciding. So the main scale, because 0 is crossing 42, so main scale reading is 42, and which one is coinciding with the main scale division, that I have to note it down while I am moving in clockwise direction. So I will note down the main scale division here and the vernier scale. Then I'll make the total. So main scale plus vernier scale multiplied by the least count, I'll get the total reading. Okay, so this is my clockwise rotation. Now what I have to do is I have to go to the position of analyzer. I have to go to the position of analyzer 180 apart from the first setting. So while I am moving clockwise, this is also clockwise. So this is my first clockwise reading, and then I have to add 180 degree clockwise. So like I have my first position of tint at like 42 degree, then what I have to do, I have to add 180 into 40. So I had 180, 44. So 4, 2, 224. So I'll go for clockwise direction, and this is my, here you can see where 210, this is, so I'll look for 244. Okay, let me see it. 230, 10, 20, 30, 40, and how much I have to go is 224. So then I'll go for 210, 220, and this will be, let me show you that. Okay, this camera is, so you can see around 224, I have fixed it to 224. So this is 180 degree apart from my first position, which was 42. So this is, while I am moving in the clockwise direction, so this around here, my second position of the tint will be here. So you can see that the first position of tint while I was moving the clockwise direction was at this position. Then the second position of the analyzer 180 apart from the first setting. So this is my analyzer. So the position of the analyzer, which was at 44 or 42 and 180 degree apart. So at the clockwise direction, I will have to find this clockwise rotation, the tint of passage at 180 degree apart. You can see this. This will be 42 and then 180 degree apart. The second tint of position will be here. That means while moving from this position to this position, this tint of position was at like 42 degree, okay, main scale. Then while moving in the same direction, clockwise direction, I'll again this will change to this, and then from this I'll have this position going to again to the first position, to the black and to the white. Then again at this position, which will be 180 degree apart from this position, I'm going to have the equal brightness, which will be the passage of tint. So this will be 180 plus 44 to around 224 degree, which was like 42 degree. So around this, I'm going to get again the tint of passage in the clockwise direction from this position, which is 180 degree apart. Okay. Now, what I have to do is I have to go the anti-clockwise direction. So till now, what I have to do is my first clockwise direction reading and 180 degree apart the second clockwise direction degree. So this is my first, this is my second. Now I'll move, like I was moving in the clockwise direction, now I will move in the anti-clockwise direction. So naturally, if I move into anti-clockwise direction, here when I will reach here, then again I am going to get the passage of tint. Okay, around this 44, 42, I'm again going to get the passage of tint. You'll see here the equal brightness. So I'll write that reading while moving from anti-clockwise direction here. Okay, at this position. Okay, so this will be my first reading, this will be my second reading, and while moving anti-clockwise, this will be my third reading. And then when anti-clockwise reading is, when I reach here, then I'll again move anti-clockwise direction, which will be 180 degree apart from this. So this is my anti-clockwise direction, that will be 180 degree apart from the first setting. So again, I'll keep on moving in the 180 degree apart in search of the tint of passage. So I'll keep on moving here, and then again naturally, if I'll reach around 224, 226, which was like 180 degree apart from the first tint position, I'll again going to get the passage of tint. So this will be my fourth reading. Okay, so this is very important, which reading I have to write where. So this will be first, and then second, and then anti-clockwise from here to here, and then anti-clockwise from here to here. Okay, so naturally this reading and this reading going to be same, because while moving clockwise, I over here and from here while moving anti-clockwise I'll again reaching at this position. So these readings are going to be equally at the same position. So then I'm going to get the mean of A plus B 2 and the mean of C plus D, this will be 2. So this is the reading. This we can take it for like 1 and 2 times or 3 times just to confirm it, and then this is for the water solution. The same thing we have to do it with the sugar solution. This was my water solution. Now I'll change the tube in which I have a sugar solution in the same volume. So I'll put the sugar solution here, I'll cover it. Okay, then what I'm going to do the same, observation table. But the difference here is when I'll see. So before doing this, like you just pull it out. So before putting this, once again you try to make it empty and fix it like this, and then do the same procedure that by looking into it, like try to find the same brightness as we did earlier, and then the position when we see the same brightness out of this, then you put the tube here, okay, and then close it. Then the moment, the difference between the water and this sugar solution tube is that when you will see into the eyepiece, like in place of this black and white position, you will see the pink and blue color. You will see the pink and blue color instead of white and black. So the scenario will be same. This side will be pink or this side will be blue, and then if we'll go on doing the rotation, and if I'm doing the rotation clockwise or anti-clockwise, I will see that the two color changes, and in between this you will either get a position of equal brightness of the pink or the bluish color. Okay, so that will be written here in the separate table for with the water solution or with the sugar solution. The first reading, similarly I'll keep on moving 180 degree apart from here to here. Similarly, so I'll get the clockwise 180 degree apart, and then anti-clockwise and the clockwise. The procedure will be same like we did with the water solution. Procedure will be same for the cane sugar, but the only difference will be this: the color of this black and white with the water will become pinkish and bluish with the sugar solution. But all the observation, the procedure of the observation will be same. So as you can see that. The same you have to make the same table for the sugar solution, and then you have to find this A prime for the sugar solution, which will be A plus B by 2, and the B prime, this will be C plus D by 2. And then when you do this, the rest of the calculation is simple. Very simple. So the mass of the sugar dissolved, like whatever we take in our is 10 gram, and then angle of rotation theta. Okay, so theta is like A prime when you have this A prime is A plus B by 2, and B prime is A plus C plus D by 2 when we have the cane sugar solution, and then A and B when we have the water solution. So you get A prime minus A plus B prime minus B divided by 2, and then you get this angle here, theta. Okay. Now I'll use this theta here in the solution, and the volume is like we use 100 cc of the volume, and the mass is 10 gram, and the length is, we use the length of this tube is like 17.5 centimeter, so this will be 1.75 decimeter. So now we have all the quantities here, and then we can calculate the specific rotation of this cane sugar, which will be in the unit of degree, decimeter, and gram per centimeter cube. So that will be at room temperature. Normally you calculate the value and write into the results. So this is a very simple experiment and just you have to keep the track of the passage of tint, that while moving clockwise direction or anti-clockwise direction, you have to see that when the color changes, and between the change of the two halves of the color of the circle, you have to be very careful that in between about the tint of passage, where the two colors are getting mixed together and the same brightness is there. This is what about all about the specific rotation of the cane sugar. And once again, you can see this is my source, this is my biquartz spectrometer, which and the tubes which we are going to use in this experiment. And the result, and there are certain precautions and sources of errors are there, so you can go all these through from any book or internet. Thank you.